Hello, today we are going to continue with our lecture series on Laplace's equation, spherical polar coordinates. And we begin the lecture with yesterday's, whatever we left yesterday. So yesterday we were doing a problem of conducting sphere placed in a uniform external electric field, and we were trying to find potential outside the uh, conducting sphere. So this is what we were doing, trying to do. Okay. So if we were trying to do this particular thing, and what we were trying to do, I told you that this particular conducting sphere is kept in an external electric field, and you know that electric lines of force enter normally to the surface. So these kind of lines you can see. Overall, electric field is along the z-axis. Electric field is along the z-axis. Also understand that usually what used to happen, that potential used to get become potential used to be in zero as r tends to infinity. But here in this particular case, since here, okay, so like here, this was a uncharged conducting sphere. Uh, like you can take it as a uncharged metallic sphere also. And if it is placed in external electric field, what was happening? There was some induced distribution of charges here. So, for example, I know that if my charge is if my electric field is in this direction, my positive charge will be pushed on the upper hemisphere, and in the lower hemisphere you can have the collection of negative charges. Okay, so electric field in general has been written as E naught k cap, and our inquiry was to find potential outside the sphere. Okay, we wanted to find the potential outside the sphere. Okay, and minus dv by dz is equals to E naught, and vz will give you minus E naught z plus c. Now what needs to be seen is that your here z in spherical polar coordinates can be written as r cos theta, where r is the radial coordinate, where r is the radial coordinate. Understand that as r tends to infinity, this will go towards infinity. So as now you cannot say that your outside potential is completely governed by this potential, because as r tends to infinity, it cannot be tending to infinite. There should be some terms in ALs also which must exist in order to completely define potential outside this sphere. So in general, what I've done now, in this case, we took that we took two conditions. One of the condition was as r tends to infinite, your potential should as r tends to infinite, uh, your potential is given by minus E naught r cos theta plus c. Even as r tends to infinite, this is your potential. So we compared and we got the value of a naughts and a1, a naught, etc. And if we want to find that on the surface, because this is a metallic sphere or this is a like conducting sphere, so the surface is an equipotential surface. So surface being an equipotential surface, we took something called as phi naught. And overall, we could understand that when we were expanding the total constant term, you can also evaluate B naught also. But overall, write this B naught by R plus C as some constant K. This will be some phi naught. And remaining terms we also identified. And we identified that potential outside anywhere can be written as phi naught minus E naught R cos theta plus E naught upon R cube R, small r square cos theta. And this, see, in general, if the sphere was not present, this was your potential. Now, because of the presence of the sphere, what would happen? There would be some induced distribution of charges. So because there would be some induced charge distribution, and because of this, there will be some induced electric field, which will modify your potential for sure by this additional term. So this is a modification which has been brought about by induced electric field inside. And overall, very comprehensively in a compact form, I can write my V as a function of r comma theta in this way. And it's very easy to find that electric field vector would be equals to minus of grad of V. And in general, this is like it depends on r and theta, so I've done this way. And overall, I've been able to identify that my electric field is in two components, that is r cap and theta cap. That is, one of the electric field is along the radial direction, another radial field is the theta cap direction. And we were trying to find what is the total surface charge density. The surface charge density just outside a conductor is normal component of electric field epsilon naught. So in general, by employing the necessary boundary condition, we can find that induced distribution is given by 3 epsilon naught E naught cos theta. And we were trying to find upper charge on the upper hemisphere and charge on the lower hemisphere. So what would be the charge on the upper hemisphere? It will be sigma, and we'll take some ds here. Ds will be what? If the radius is of r radius, then this will be r square sine theta d phi. So I'll write somewhere r f missed. So this will be like 3 epsilon naught E naught r square. And this is cos theta sine theta. You can write sine theta cos theta as sine 2 theta. So I can write sine 2 theta d theta and divide it by 2. So I'll divide it by 2. put it outside, theta lying from 0 to pi by 2, and then have this integration like 0 to 2 pi, and this is d pi. So overall, I'll get 3 epsilon naught E naught r square by 2. And you can understand the sine theta integral will be minus cos theta, and cos 2 theta I will write cos 2 theta again by 2. So for example, I had written 2 here divided by 2. So this will be sine 2 theta divided by 2. And overall, you have to take the sine 2 theta integral is minus cos 2 theta integral from theta equal to 0, theta equal to pi by 2. And then you can write 2 pi as well. So overall, this will be a charge on the upper hemisphere. You can expect that charge on the upper hemisphere should be positive and charge on the lower hemisphere should be negative, which is indeed clear from the charge density also. See, charge density is given by 3 epsilon naught E naught cos theta. So in the spherical polar coordinates, your upper hemisphere and lower hemisphere. Now see, here, this is how you define your theta in spherical polar coordinates, and phi governs this kind of rotation. So basically, if theta lies from 0 to pi by 2, if theta lies from 0 to pi by 2, I will be talking of the northern hemisphere. If my theta lies from pi by 2 to pi, I would be talking of southern hemisphere. And you can see that in the northern hemisphere, since theta lies between 0 and pi by 2, sigma is positive. And in the southern hemisphere, since theta lies between pi by 2 and pi, the sigma would be negative. And which indeed is the case from physical intuition. Also, we know that since electric field is in the k-cap direction, so it will push the positive charges on the upper hemisphere. So you will have a positive charge, positive induced charge density in the upper, and on the lower you should have a negative charge density, and which you can see from here as well. Is that clear? So overall, I can expect that my total charge on the upper hemisphere would be positive, and equal and opposite charge would be there on the equal and opposite charges would be there on the lower hemisphere, barring that the sign would be sign would be the contrary. That is, on the upper hemisphere it is positive, then on the lower hemisphere it would be negative. So overall, you can understand your like this Q upper would be equals to what? I think this would be 3 epsilon naught E naught r square upon 2. And then you can write this cos 2 theta cos 1 by 2 1 by 2. This will be like 2 divided by 2 is 1. So this is 2 pi. So overall, you will get this cancellation. This will be like 3 pi epsilon naught E naught into r square. Clearly, this is positive. So your charge on the upper hemisphere is positive, and equal amount of charge would be there on the negatives on the lower hemisphere, but in the negative side. So I think this problem is solved. Now today we are going to move ahead. Just try to do one problem so that just try to do one more problem so that you get thoda sa haath sahi chale. So for example, if I'm giving the sphere, the surface of the sphere, the surface of the sphere has a potential given by phi is equals to phi naught cos 3 theta. Okay. And if there are no charges outside the sphere, if there are no charges outside the sphere, we have to obtain the potential anywhere outside. Obtain the potential anywhere outside. Obtain the potential anywhere outside the sphere. So all you are given is that your surface of the the surface of the sphere has a potential phi naught cos 3 theta. So this surface has potential phi naught cos 3 theta. This is your potential. Okay, this is your potential which is given on the surface. Now you are asked what is the potential anywhere outside the sphere. So you know that your summation like AL, and you have this. See, you can see that your potential has only theta, so it does not have this high symmetry. So you can write that this problem has an azimuthal symmetry. So you can see that there is no phi dependence. So this particular problem has an azimuthal symmetry. And so therefore the Laplace's equation anywhere outside, because see, anywhere outside it is written that there are no charges, so your del square V would be 0. And you can write that you can say the solutions to this the potential anywhere in general can be written as this way. And we know that anywhere outside the potential would be governed by this particular solution of the potentials. This governs your potential anywhere outside. So this governs your potential anywhere outside. Potential outside. Okay. So this governs your potential outside. So what you do, you just take this particular thing. So your summation L equals to 0 to infinite BL upon R raised power L plus 1. This forms your potential anywhere outside. This forms potential anywhere outside. And we know that as R tends to capital R, it will give you what? It will give you phi naught cos 3 theta. And if I correctly remember, the formula for cos 3 theta is, I think this is, even if you forget, you can do like calculations in your examination from your initial trigonometric classes. You know that you can write it as cos 2 theta plus theta, and then you can take this. So don't worry about it. So like अगर cos 3 theta भूल भी जाओ एग्जाम में, क्या करना, cos 2 theta plus theta करके cos a plus b का फॉर्मूला आता है, फटाफट करना, you will be able to get the formula. Don't worry. So this is how you write your cos 3 theta, and you see that there is a cubic term here. So at least p3 तक तो जाएगा ही जाएगा. At least p3 तक तो it will go on, like at least till p3 to 2. So what I would do is I would simply take BL upon R raised power L plus 1, and you have this PL cos theta, and summation implied, you know that summation is there, and then you have this phi naught, and you have this 4 cos cube theta, and then you have this minus 3 cosine theta. Okay, now all you need to do is expand this particular side, so you will get P naught upon R, like plus B1 upon R square, and then you have this cosine theta, and then you have this B2 upon R cube, B2 upon R cube, and this is 3 cos square theta minus 1 by 2, and then you have this B3 upon R raised power 4, and then you have, I think, क्या होता है, 5 cos cube theta minus 3 cosine theta divided by 2. So all these things are there. All you need to do is just compare these terms and just let me know what will be the coefficients. Okay, so you have this cos cube theta here, and this is minus 3 phi naught cos theta. I'm giving you a minute. Try to solve this thing and try to solve this B naught, B1, B2, B3, and B. So that we'll be able to. If there is a doubt, if you really think that the like B5 can come, you can add B5. But the point is that there's no such term called as cos 5 theta. So in any case, B5 theta would go to 0. But still, if you have doubt, you can expand till that also. I have no issues. But eventually, you'll find that these are the like required expansions to be made. So what you can do, you can put them together. So for example, the constant terms, I'm going to put them together. So this is my constant term B naught by R, and then you have this minus B2 upon 2R cube, and then you have this whatever is like linear terms, you can put all together, and then you have this B2 upon R cube, and this is 3 by 2, and this is cos square theta. This is what I was telling. So for example, you do not have cos squared theta term here, so your B2 would go to 0. So you do not have B2 here. So this is what I was telling, that if you do not have the cos 5 theta term, then B5 would be 0. So if you think that the Legendre's polynomial P5 contains a cubic term as well, and why I have not written it, because I know that there is no such cos 5 term, like cos ki power 5 theta hai nahi, so you do not have to, you should not bother about it. Still, if you bother about it, you can do expansion till P5. But in examination, like if people are preparing for some TFR or net examination or just examination, I would say that at least P4 tak, at least you should remember. And people who are right now in MSc, try to get into like good institutes. At least TFR or just clear karo, so that you remain in good research institutes. So that would be good for you. Okay. So overall, let me write all these things. So you have this, I think, where is this cos cube theta? Here is this cos cube theta. So I can write this cos cube theta as 3. I think this is 5, and then this is B3. And then you have this 2 times R raised power 4. And then you have this cos cube theta, and this cos, here you have 4 phi naught cos cube theta, and minus 3 phi naught cos theta. So overall, I can understand that this is my expansion. And if this remains my expansion, what I can do is I can equate both sides. So I can equate both sides, and I can find B3. So my B3 is I think if I correctly solve it, then B3 would be from here. I mean, compare these two up. So this will be, I think, 8 over 5, and then this will be some phi naught, and I think this will be some r raised to power 4 also. Is that clear? So this is your V3. 8 by 4 phi naught into r raised to power 4. I think it is fine. And then you have to equate these, like this B2 is going to go to 0. Forget about it. All you have is B1. So your B1, kahan chala gaya? Here, B1. B1 is there. So your B1 upon r square cos theta. So B1 upon r square will give you minus 3 phi naught. So your B1 is okay. There is another component here, like cos linear terms. There are two linear terms. Sorry. There are two linear terms. One linear term is here. Another linear term is here. Okay, so two linear terms. So you have two linear terms. So B1 upon r square minus B3, 3B3 upon 2 r ki power 4. This all term is equals to minus 3 pi. Is that clear? Because here is also a linear term. Don't forget about it. And this B3 is not going 0 because you have a cos 2 term there. So ये थोड़ा सा ध्यान रखना, otherwise you get a wrong answer. ठीक है, तो देखो क्या कर सकते हैं. B3 upon r की power 4 is 8 by 5 phi naught. So I'll write 8 by 5 phi naught here. Is minus 3 phi naught. So what all you will do is take this there. So you'll get, I think this is B1 upon r square is, I can write as 24 upon 10 phi naught minus 3 phi naught. This is minus 6 by 5 and minus 6 by 10, I think. So 30 means 6 by 10. So I can write it as minus 3 by 5 phi naught. And overall, I'll find that my B1 is nothing but minus 3 by 5 phi naught r. So such questions are usually asked in examination. Like these are the questions that are asked. So B3 you know, B1 you know. So now you can write here potential very conveniently. So potential would be equals to what? So potential anywhere outside can be written as summation PL upon r raised to power L plus 1 PL cos theta. And now you are already aware that what is your B1 and what is your B3 and all sorts of things. So you can just place L equal to 1. So if you place L equal to 1, because L equal to 0, BL is 0, and L equals to 2, BL is 0, L equal to 3, you have some non-zero term, and then for all other L's, your BLs are 0. So all you have in expansion the terms of B1 and B3. So if you have this term B1, so what you'll get, I think this is, if I'm not wrong, this will be like minus 3 phi naught, and then there would be some r square, and then there would be some 5, and then you can have this 1, this will be r square, and then you have this P1, so this is, I think, simply cos theta, plus 8 by 5, you have this phi naught r raised power 4 divided by P3 term है ना, या P3 term होगा तो यहाँ पर भी क्या आएगा r raised to power 4, and then you have P3 cos theta. P3 cos theta is 5 cos cube theta minus 3 cosine theta divided by 2. I hope this solves your problem. So this is what it is. Is that clear? I mean, ये कर पाओगे ना exam में आप? And mind you, these questions are being asked time and again in examinations. Like you cannot skip this topic at all. Even if you don't do entire rigorous derivation, you should at least be knowing the solution part. At least solution part should be very much clear to you. Is that clear or is that not clear? Should I give you another question? Like all these questions are the same. Like अगर तुम देखोगे भी तो mostly these are the questions that are asked. Therefore, I'm not doing it in such details. मतलब only thing is कि इसके अलावा कुछ और पूछ लेंगे. मतलब only thing is कि potential के form change होते रहेंगे on the surface, and you will be asked potential inside and outside. So that forms a very well posed problem. Is that clear? Yes or no?
Yes.
फिर सेकंड टर्म में r क्यूब आएगा नीचे.
सेकंड टर्म में r क्यूब आएगा. हाँ यार देखो
ये लास्ट सॉल्यूशन में
देखो ये B3 था बेटा, है ना. दिस इज B3 होने के कारण यहाँ 3 आएगा, तो हियर इट विल बी r की पावर 3 प्लस 1. दिस विल बी r की पावर 4 only. Okay ना, because B2 was 0. Okay, so I hope it is clear. देखो till now what we have done, we were doing a problem where we had a azimuthal symmetry, and because of the azimuthal symmetry our solutions were in the form I have stated already before. And most of the problems are like all of the problems we have done till now, we were specified potential on the surface. Okay, we were specified potential on the surface. Now the question arises that instead of potential, if surface charge density is specified, if surface charge density is specified, then what to do? Okay, now instead of potential, if surface charge density is specified like on the surface of the sphere, and right on the surface of the sphere, then what to do and how to approach such problems. Okay, so instead of potential, if like surface charge density specified. So now I'm coming back to the newer sort of problem. Like the solutions will remain the same. The only thing is now your boundary conditions are specified in terms of your like charge density on the spheres. For example, this is your sphere, and I think if I just write it over here, so if if surface charge density specified on the surface is given by sigma naught theta. So this is your surface charge density. So I can write that there's a specific surface charge density, specified surface charge density on the surface. So on the surface, if the charge density is specified as sigma naught theta, and this is your sphere of radius capital R, then we want to find what will be the form of the potential anywhere inside and outside. So then we are interested in, finding the forms of potential inside or outside. Okay, then we are interested in finding the form of the potential inside or outside. Is that clear? So, although we can find it by direct integral method also, like we can take it as v is equal to say q upon small r integral, and instead of q, I can write sigma ds. But we know that we already know the solution form, so why not exploit that? Okay, why not exploit that? So obviously one can take this route also. One can take this k dq upon integral r, and then instead of sigma, one can write sigma ds, and all those things can be done. But like this is one approach that can be done. But since we already know that your del square v, if it is equal to 0, the solutions are of the form al, and inside if I want to write this will be my like summation is implied. Inside, if I want to write, this is my potential inside and this is my potential outside. So I already know my form of potential. All I need to know is, given the boundary condition, all I need to know is what are my ALs and BLs, and I can simply state my potential. Okay, so this is certainly easier way right now. For standard 12 people, this would be difficult because they don't know about Legendre's polynomial. Probably you people also don't know that much about Legendre's polynomial. I'll let you know. For example, I mean, all you know is the form, and that solves your problem right now. For example, while we'll be doing the generating function part, we'll be exploiting the generating function. While we'll be doing the multipole expansion thing, then we'll be concentrating on the generating function part of the Legendre's polynomial. So possibly in bits and pieces, I'm going to cover this Legendre polynomial in physics side, and mathematics side we take a complete one lecture, and I think this will be all. This will be done in one lecture. It will be done. Okay, now. So del square v equal to 0 gives you both of these conditions, and like del square v equal to 0 would give you both of these solutions depending upon where you're interested in, right? Like for example, you're interested inside, this would be a potential. You're interested outside, this would be a potential. Okay. Okay. So now first thing that comes to our mind, that one thing is for sure, that is our potential must be continuous at. This is something that I've already done. Potential must be continuous at r equals to capital R. So one thing that we already know, that our potential should be continuous at r equals to r. That implies what? That implies your AL r raised to power L PL cos theta must be equal to what? It must be equal to summation PL upon r raised to power L plus 1 PL cos theta. Is that clear? Since your potential is continuous on the surface on a conducting surface, even if it contains sigma, it has got no problem. But electric field, the normal component would become discontinuous. All these boundary conditions, again, I'm going to discuss in detail later on. But I assume that since you're in MSc, at least you've done this thing. If you have not done this thing, if you cannot remember this, just remember whatever I'm stating right now as a fact. Okay, so potential must be continuous at r equals to capital R, and this serves you this kind of thing, because see, potential inside is given by this, potential outside is given by this. So what does it mean? So it means that r is less than r, and here you have this r is greater than equal to r. You can place r anywhere. So point is this: both of these conditions, both of these potentials should be continuous at r equals to r. So this would give me this thing. This would be this. I hope it is clear. And if I compare both of the side, I will get a relation between ALs and BLs. So what would my BL? BL would be, I think, AL r raised power 2L plus 1. So this is one of the conditions that one needs to remember. Okay. Okay, the most appropriate way to do this would be to just integrate both of the side by PL dash cos theta and apply the orthonormality condition, apply the orthonormality condition, that is PL dash dx is equals to 2 upon 12 plus 1 Dirac of, canonical delta LL dash. But fine, I know that my PL forms a complete set, and if it forms a complete set, I can expand on both sides. And if I expand on both sides, so if I compare both sides, I can do that also. So that is equally good. So BL is equal to AL r ki power 12 plus 1. Is that clear? Okay.
So this condition is valid for all the regions where Laplace equation is satisfied, right?
Right.
Okay, sir.
See, understand my point. जो हम करते हैं, for example, देखो, this is a condition that we are finding, that we know from our boundary conditions. So in boundary conditions, if you have a surface which contains a charge density sigma, and here you will find that your potential outside and inside would be potential would be continuous on this particular juncture, like on the surface. However, since sigma is glued over it, so your electric field normal component would be discontinuous. So these two conditions we know from our boundary condition side. Boundary conditions of electric field, like we study na कि electric field का perpendicular component, tangential component.
Yes, sir.
है ना? तो electric field का जो perpendicular component होता है, it becomes discontinuous on a surface which contains some surface charge density, and that quantum of discontinuity can be given by sigma upon epsilon. And similarly, if you find that your potential remains to be continuous on the surface, so this gives you one condition which is not necessarily not necessarily given also, but it is necessarily implied. Like we know that this is a conducting sphere, it will contain some sigma, fine, but overall understand that this would be, the potential would be continuous on the surface. So this is clear. I mean, this is clear, I hope. And I have not taken that electric field case. For example, when we were discussing electric field, external electric field, then there was certain difference, because when electric field is placed, then this condition cannot be, this sort of thing I cannot write, because if electric field is there, then this will be like I told you that even as our tension fit, your potential was being infinity. So in that case, we cannot bifurcate our solution into two halves. So I hope it is clear. The other part would give me, as I have written, that your electric field suffers, like the normal component of electric field suffers a discontinuity over the surface containing a surface charge density sigma. So the surface contains, if surface is glued with the surface charge density sigma, the normal component of the electric field would suffer discontinuity. So normal component of electric field would suffer a discontinuity, and this discontinuity suffer discontinuity, and this discontinuity is given by, I think, sigma over epsilon. Okay, is that clear? So I can write that my E perpendicular outside minus E perpendicular inside is equals to sigma upon epsilon. Is that clear? And what I can do is, instead of writing E perpendicular outside, what is the normal component to the radius? What is the normal component to the sphere? It is the radial component. So if you see, so this is the tangent, here it is, this radial component is always perpendicular to the surface of the sphere. So what I can do, instead of writing this, I will write minus dv out upon d small r at r equals to capital R. You can write plus here, minus minus again plus, so it will be like dv out, sorry, dv in divided by dr at r equals to r minus, this will be like sigma upon epsilon. Is that clear? देखो इलेक्ट्रिक फील्ड क्या होता है, माइनस ग्रेड वी, सो इलेक्ट्रिक फील्ड आउट वुड बी व्हाट, डेल वी आउट, what is the normal component, normal component is radial, this is at r equals to r plus, and this negative will be there, and this negative would become positive. Is that clear?
Yes.
I hope it is clear. ठीक है, अब देखो what is potential outside, so potential outside is given by I think bl upon r is power l plus 1, and then you have this pl cos theta. Okay, and if I write what is my del v out upon del r, so del v out upon del r, even if you place this summation also there, all these things does not matter, only derivative we have to take over this. The derivative over this would be what? So derivative over this would be, I think I should write it in minus l plus 1. Here it would be minus l plus 1, and then there would be some bl upon r ki power l plus 2, because this is minus l minus 1, then derivative minus 2, and this will be like pl cos theta. Is that clear?
Yes.
Okay, so I think this would be the derivative, this would be the derivative, and we have to evaluate it at r equals to capital R. So I will simply write here summation l equal to 0 to infinity, and then you have this minus of l plus 1, and then you have this bl upon r ki power l plus 2, and then you have this pl cos theta. And similarly, if you find this, I think del v in upon del r, so del v in upon del r would be, I think this is simple because you don't have a, अच्छा यहाँ पे कुछ गड़बड़ हो रही है ना, यहाँ पे there would be some plus, and then there would be some, हाँ बेटा,
सर फर्स्ट टर्म में प्लस,
देखो del v out, electric field outside would be given by del v upon del r, negative तो होगा ही ना, because electric field is given by minus of grad of v.
सर डेरिवेटिव में भी नेगेटिव,
अच्छा सॉरी, हाँ एक डेरिवेटिव में भी नेगेटिव, सॉरी सर, ओके सॉरी, okay, and the second term will have like al, then there will be some r raised to power l minus 1. Okay, r raised to power l minus 1, sorry, I'll place r raised to power l minus 1, and then there would be some pl cosine theta, and this will be equal to sigma upon epsilon. Is that clear? यहाँ तक समझ में आया नहीं आया?
यस,
Okay, okay, now you already know that your bl is given by al, और ये कहाँ गया, bl was given by al into r की power 2l plus 1, याद है ये चीज? So you can readily use this condition and put it here. Okay, so instead of bl you can place al into r ki power l plus 1. So this is l plus 1, here you can place al into r ki power 2l plus 1, and 2l plus 1 will become, I think, l minus 1 if you take this, and then you have this pl cos theta, and then you have this l al, and I think this is r raised to power l minus 1 pl cos theta, and this all is equals to what? This all is equals to sigma over epsilon. Is that clear? So if you add them up, this is L, this is L, this is 2L plus 1. So this is 2L plus 1, and there would be summation going all over. R is per L minus 1, and this will be PL cos theta. And this is, I think, equal to sigma over epsilon. Is that clear? Now I know in order to extract, in order to, sorry, AL bhi to reh gaya. In order to extract this AL, what I can do? I can multiply both of the sides by PL dash cos theta and sin theta d theta. That is something that you know. And this sigma was given on the surface. I know on the surface because we are placing r equal to capital R. So now instead of sigma, I can write sigma naught theta. So I can write sigma naught theta because we have placed r equals to capital R. So on r equals to capital R, we have the sigma naught theta described. Now what you can do, you can multiply both sides by PL dash cos theta, sin theta, d theta, and integrate it from 0 to pi. In order to exploit the orthonormality conditions of the PL, we'll do this. So overall, we'll be able to understand that this is like 2L plus 1. And I yesterday also told you that only for L equal to L dash, this integral would be a non-zero integral. And this would give me 2 upon 2L plus 1. And then I think like all these things, yesterday itself I did it. And here you will have the sigma naught theta. And I think there would be some epsilon naught here as well. And then there will, sorry, 0 to pi. And this will be like PL cos theta, sin theta, d theta. So most general expression to your AL, and once you find your AL, you can find BLs. Once you find your AL, you can find your BLs as well. AL would be equals to what? AL would be equals to, I think this gets cancelled, so forget about it. Your 2 is here, so your 2 will come down, and this R is for L minus 1 also come down. 2 R is to power L minus 1. And there is epsilon naught also, so I'll write epsilon naught somewhere here. Integration from 0 to pi. And I think there is sigma naught theta written, which is the surface charge density glued over the surface. And this will be like PL cos theta, sin theta, d theta. So this is how you're going to write your expression of AL. And once you know your AL, you can readily find your BL as well. And once you can then find your potential inside and outside. Like, is it clear? I mean, this is these are the approaches that we are going to take. Certainly, this is the most general way of writing things up. Probably this may be asked in interview. This is something that I don't expect an examination to be asked. But overall, this remains to be the approach. It exploits two of the boundary conditions. One, that potential must remain continuous at the boundary, and another one is that the normal component of the electric field over the conducting surface suffers a discontinuity with sigma upon epsilon naught, because conductor in any way contains the charges, like it contains the charges on the surface only. So therefore, it suffers a discontinuity. This is something that I told you also with the example of like electric field for conducting shell. So electric field inside is 0, electric field outside is kq upon r square, and I calculated this kind of discontinuity using an example. Okay, is that clear? सबको समझ में आ रहा है कि मैं बोले जा रहा हूँ, nobody is getting anything? ऐसा तो नहीं हो रहा ना? So how many people are there? Kriti has gone. Saloni is somehow resisting. अल्पना, भारत, किसी को कुछ समझ में आ रहा है, नहीं आ रहा?
Yes, sir.
हाँ भैया,
सलोनी को समझ में आ रहा है, नहीं आ रहा?
आ रहा है सर।
चलो बढ़िया, धन्यवाद. So ठीक है. So एक काम करते हैं, just because there is a lack of time, I'll just give you a simple example, and you just find that particular what would, for example, if sigma naught theta is given as k cos theta. If sigma naught theta is given k cos theta, that is, if sigma naught theta is equal to k cos theta. This I'll solve in the next lecture, but I'll just write the question. If sigma naught theta is equal to k cos theta is glued over the surface, of a sphere, then find the potential inside as well as outside. Find the potential inside as well as outside, and take the radius as r. So take the radius as r, if it is required anyway. So take the radius r. I hope it is clear. So you just try to do this, and I'll meet you in the next lecture. You have a minute or so. So I'm ending this session. I'll meet you in the next session.